IP Tech Talk. Hello everyone, and welcome to IP Tech Talk. Today, we're going to talk about the differentiators of Wi-Fi 6. As introduced in an earlier video, Wi-Fi 6 is the latest generation of Wi-Fi and adopts many key technologies from 5G, such as MU-MIMO and OFDMA. This allows it to deliver higher Wi-Fi performance with ever greater speeds and capacity, as well as all new functions. The differentiators of Wi-Fi 6 that I want to talk about today are higher transmission speed, super high concurrency, and super long standby. Okay, so let's look at these three differentiators of Wi-Fi 6 one by one. First is higher transmission speed. As network technologies continue to develop, bandwidth-hungry services such as 4K and HK HD videos, as well as VR and AR, are booming across all industries, with the goal of bringing superb service experience to users. The trouble is, legacy Wi-Fi networks can no longer sustain these services. Instead, Wi-Fi networks with much higher data transmission speeds are urgently needed. To put into perspective the kind of bandwidths that are needed, 4K wireless projection, AR and VR, and interactive gaming require 50, 60 and 200 megabits per second bandwidth respectively. Service development is a core driving force that accelerates data transmission on a Wi-Fi network. If we look back at the development path of Wi-Fi technologies, we can find that the Wi-Fi industry undergoes a technological revolution every 4 or 5 years, with each revolution aiming to achieve a higher data transmission speed. And Wi-Fi 6 is no exception, driving up data transmission speeds to as high as 9.6 gigabits per second. Okay, let's now look at this figure to compare the transmission speeds of each generation of Wi-Fi standards. As you can see, the maximum data transmission speed of Wi-Fi 6 is 1.4 times that of Wi-Fi 5 and 8 times that of Wi-Fi 4. MIMO technology started to be supported from Wi-Fi 4 or 802.11n. This is also a turning point in the Wi-Fi industry, as this is when the maximum speed of a single spatial stream and the maximum device speed started to be distinguished. The maximum device speed is calculated by multiplying the maximum speed of a single spatial stream by the number of spatial streams. Note that the upload and download speed of Wi-Fi 6 are symmetric and both can reach up to 9.6 gigabits per second. This differentiator is crucial in today's era of individual WeMedia and live streaming. It also helps to support many IoT applications, such as VR and AR, unmanned driving, and telemedicine. Wi-Fi standards prior to Wi-Fi 6 can be seen as supplementary to wired access. Estimates show that the download volume exceeds the upload volume for these standards, and so their downlink speeds are much higher than their uplink speeds. This kind of asymmetric access mode cannot meet the needs of IoT as we enter the era where all things are connected. The second differentiator is the super high concurrency capability. Before Wi-Fi 6, there was no special emphasis placed on the concurrency capability. From Wi-Fi 6, this becomes a top consideration. This is because IoT technologies require masses of IoT terminals to access the network through Wi-Fi technology. This means that WLAN channel resources become increasingly insufficient. For example, in large outdoor public places and high-density stadiums, there could be tens of thousands of users using the same network ID. What's even more challenging is that the number of users who need to access the network concurrently also increases, making the multi-user queuing and congestion issue more severe. This leads to two problems. First, the per-user network access speed drops sharply. In response, the Wi-Fi network adopts the CSMA-CA mechanism to coordinate user conflicts. With this mechanism, before transmitting data, a user listens to a radio channel and transmits data only when no other user uses this channel. As conflicts get worse, resource competition between users will cause a sharp decrease in the per-user network access speed. For example, if 10 users contend for a radio channel, the bandwidth for each user will be just 1/10 of the total channel bandwidth. This is why we sometimes find that the Wi-Fi signal is strong, but for some reason we cannot upload a video file. The second problem is that the data transmission latency increases drastically. The latency of Wi-Fi 5 remains 30 milliseconds under optimal conditions. In other cases, for example when a large number of users access the network, fierce resource competition between users extends the service latency to 200 or 300 milliseconds, or even several seconds, deteriorating user experience for latency-sensitive services. Let's take AGVs in the intelligent warehousing industry as an example. They look like robot vacuum cleaners and are very flexible and smart. In a high-density environment, they will stop working once they fail to receive data packets due to excessively long network latency, leading to AGV disorder or even severe production accidents. In such a high-density environment, improving the transmission speed of a single AP is no longer a top priority. Instead, more emphasis must be placed on how to shorten the queue duration when multiple users contend for Wi-Fi resources, as well as how to reduce the network latency and improve the overall efficiency of the Wi-Fi network. This is where Wi-Fi 6 comes in. Let's now take Huawei Cloud Campus solution as an example. With the latest Wi-Fi 6 products deployed, this solution improves the average bandwidth per user and the number of concurrent users fourfold, and provides an average service latency of 20 milliseconds. With Huawei's smart radio technology achieving intelligent application acceleration, this solution further reduces the service latency to just 10 milliseconds. Wi-Fi 6 adopts numerous cutting-edge technologies to improve its concurrency capability. Next, I'm going to describe 3 of them. The first one is DLUL MU-MIMO, which improves spatial multiplexing from 4x4 to 8x8. With this technology, an AP can communicate with up to 8 terminals at the same time. This means that each user does not need to wait in a queue, and so reduces the transmission latency. Next up is OFDMA, which drastically increases the spectrum utilization. The communication process is similar to goods transportation. To improve the transportation efficiency, we need to optimize highways or trucks. OFDM technology can be compared to highway optimization. It divides a highway into multiple lanes, with each truck driving in a different lane. This prevents trucks from interfering with each other. And despite this, the goods loading capability of each truck is not fully utilized. Just like a truck transports only one type of goods, a channel is exclusively occupied by one data flow. To resolve this issue, OFDMA technology steps up to the plate. It can be compared to truck optimization. It divides a truck's container into multiple goods loading blocks of different sizes, so that one truck can transport different types of goods at the same time. In this way, the spectrum utilization is increased drastically. The last one is BSS coloring, which is ideal for eliminating co-channel interference. When multiple users transmit signals on the same frequency, co-channel interference may occur. This is similar to when everyone in a room speaks loudly in the same language and no one can be heard clearly, as people getting distracted by other people's conversations. If some people speak English, some others speak Chinese, and the remaining speak Japanese, they can get across their desired information clearly. This is similar to how co-channel interference can be effectively eliminated. The last differentiator of Wi-Fi 6 is its super long standby capability. As an active technology, Wi-Fi 6 will consume a certain amount of power. In the past few years, you may have noticed this. Once Wi-Fi is enabled on our mobile phones or tablets, their batteries drain quickly and our mobile phones may heat up. Before you know it, the battery is down to 10% and we start frantically looking for a charger. Why does this happen? This is because electromagnetic waves are used as transmission media in the wireless communication field, and the transmission of electromagnetic waves requires a certain amount of power. Once you enable the Wi-Fi function on your terminal, it will start to consume additional power. For Wi-Fi technologies, a major factor that affects the battery standby time of a terminal is the amount of power consumed to keep a connection, even when the terminal is not operating. This is because when there is no data transmission requirement between a terminal and an AP, they still need to send signals to each other to maintain their connection. This is why batteries of some battery-powered IoT terminals need to be replaced frequently, which is far from ideal. To resolve this issue, Wi-Fi 6 introduces TWT technology. It allows terminals to negotiate with APs when and for how long they will wake up, and then send or receive data. This technology slashes power consumption of terminals by 30%, significantly prolonging the battery standby time and life. It can be understood simply as the terminal remaining in sleep mode and waking up by the AP only when it needs to operate. Terminals can negotiate with APs the time that they will wake up to prevent terminals from unnecessarily contending for radio resources. In this video, I described 3 differentiators of Wi-Fi 6. They are high transmission speed, super high concurrency, and super long standby. Well, that brings us to the end of today's IP Tech Talk about Wi-Fi 6. Thanks for watching, and see you next time.